As was already stated, my name is Wolstrup, and I am presenting the paper 3D printed conductance-based force sensors using single Traxels. And this project was a part of my PhD project, but the sensor itself was actually made by one of my students, Thomas, who is also here today. So he can help if there's any additional questions later. Short overview of the very short presentation: introduction, theory, results, and conclusion. About as basic as it gets for an overview. So what we wanted to do was to try and say we want to make a force sensor, a resistive force sensor. We want to do it in a way where we don't have to rely on changing the material. We want to do a commercial material, in this case, a carbon-doped TPU, filament for common material extrusion printing, FDM printing, if you're familiar. And we want to see if we can make a sensor based on the geometry of our sensor as opposed to material changes. And what we wanted to do was then to take, say, what if we print a single line or a single Traxel, and then we make a geometric pattern that we control mathematically, and see if changing that pattern while varying, trying to keep everything else the same, so same dimensions, does it change between three different types of easily attainable mathematical patterns, such as a sinusoidal pattern, a circular pattern, and a triangular pattern. And the idea here, I guess I should say, was that we just printed two layers of the conductive TPU, which is black, you cannot see it here. And then we had copper plates between them for contact. So these are just going all the way through. So we just have, it's a two-pronged, just a resistor. And then we have a green TPU to support it, which is then on either side, just to give it some thickness so we can actually press on it, as you see here. And the idea is that as the pattern collapses, then there's a change in resistance, and that we can measure, and then we can correlate it to the force. So the theoretical background of this is that we use contact of restriction resistance, or basically when you have two conductors and they touch, because they're not perfectly flat, there will be surface roughness. Because of this surface roughness, we have a certain number of contact points or asperities, which are assumed to be long and cylindrical in shape. And the idea is that if you have one of these asperities, then each asperity's resistance is related to the resistivity of the material divided by the diameter of the cylinder. If you then have multiple, because they are far apart compared to their area, they are considered electrically in parallel. And because of this, we can basically just sum all the diameters to something called the contact length, LC. But of course, this is not a measurement. It is not a measurement you can do. You cannot measure this length, so we have to relate it to force. So, please, thank you. The relationship between constriction resistance and force is not agreed upon in the literature. But it was found in a paper I did for FLEPS in 2023. And basically, depending on how you model it, you get slightly different variations on the contact resistance to force proportionality. And we found in that paper from 2023 that, at least from a related sense of this one, that the one that is directly reversely proportional to force was the one that fit best with our measurements. So we printed 3 of each of the patterns to check if there was a difference in printability and how good it was between sensors, or how good the consistency was between sensors. And we wanted to see for about 50 Newton how each of the sensors behaved. So this is the sinusoid, which had quite good change in resistance. So I guess I should say we are measuring in conductance as opposed to resistance. And this is just because as we push these sensors together, the resistance drops. And in that case, it drops by a certain amount. But if you flip it to conductance, then it increases, which is more, I guess, akin to what we usually see in other sensors. So it's easier to compare to other sensors. We have a rising output as opposed to a decreasing output. Of course, it's exactly the same electrical behavior. It's just whether I have voltage over current or current voltage. However, if we look at the circle and the triangle, we can see that they have a much lower response. And while they still, to some degree, have a decent response, we could definitely use it, they're nowhere near the sinusoid. What we also did was to try to quantify the linearity of each of the sensors. So the black line you see here was just a linear fit, and then we used the R squared to see how linear it was. This is all, I should say, this is all for 5 cycles of the sensor. So this is just the results in table form. And what we can see is that the linearity over here is quite good for the sinusoid on the wall. And while it's also decent to some degree, it's not the same for the others. And also, again, the sinusoid has a much higher change in conductance. And the one that we found was the best was sinusoid 3. because while it has not the highest sensitivity, it has by far the largest linearity. It has a comparable sensitivity. Also, we can see that while they are each pattern or each file that we printed 3 times, while they are similar, there's still some process variations that gives them not insignificant change. But compared to earlier results we had where we did not know if a sensor would work or not, depending on the same file, this allowed us to have a more consistent, I guess, sensor printing. So, in conclusion, we demonstrated the feasibility of 3D printing conductance-based Hall sensors using a very common and very available process, FDM. We found no significant change in printability between the different patterns, but we found a very big difference in the usability and the performance feature of each one. The sensitivity and the linearity was best for the sinusoidal one, with a sensitivity of 0.03 bar per Newton and a linearity of R squared equals 95%. We validated that the constriction resistance theory, that's I guess at least one of them, relates to like correctly compared to our sensor, the force and conduction relationship under compression. And finally, we demonstrated that we can even use this very small single line, which is 0.4 millimeters wide, for sensor construction. And I guess I have an extra word there. So I wanted to keep it very short today because I didn't want to take up too much time. So I have a contact info there, but any questions now?